Comet 3I/ATLAS, a strange, almost alien object streaking through our solar system, has captured the attention of astronomers and stargazers alike. Its sudden appearance in 2017 as an interstellar visitor raised more questions than it answered. It's the third confirmed object from another star system, making it a once-in-a-lifetime opportunity for those studying the cosmos. This comet is unlike any we've seen before, with a hyperbolic trajectory cutting across our planetary neighborhood at an incredible speed. As it approaches the Sun, its complex composition has shocked scientists. A coma dominated by carbon dioxide, unusual gas and dust emissions, and a rich mix of organic compounds. Yet as astronomers around the world rushed to capture this celestial anomaly, something unexpected happened. At a critical moment when Western telescopes went dark due to maintenance, technical failures, or other issues, China stepped in with fresh images and data that not only filled the gap, but advanced our understanding of the comet's nature. This shift in the astronomical balance raises more than just scientific curiosity. It may signal a shift in the control of space data and in how astronomical research is conducted on the global stage. To understand the significance of China's intervention, we must first consider the extraordinary nature of Comet 3I/ATLAS. Unlike comets that form in our solar system, 3I/ATLAS has interstellar origins, passing through our cosmic neighborhood on a hyperbolic trajectory. It's a visitor from another star system, a traveler from the deep unknown of space. Its brief but significant journey through our solar system provides a rare opportunity to study an object that did not form here, making it a scientific goldmine. Scientists have been able to observe its cometary features and unprecedented chemical composition. Early observations revealed an unusually high concentration of carbon dioxide, a gas more commonly found in the atmospheres of exoplanets than in traditional solar system comets. Along with the CO2, scientists detected organic materials, water ice, and carbon monoxide, suggesting the comet had been exposed to the harsh radiation of interstellar space for eons. This bizarre mix of compounds, never before seen in a comet from our solar system, piqued the curiosity of astronomers across the world. The comet's hyperbolic trajectory made it impossible for our solar system to capture it gravitationally, meaning it would pass by only once and never return. As it passed through our solar system, a bevy of telescopes worldwide began observing it. From Hubble to JWST, and from the Gemini network to the Very Large Telescope, these astronomical giants worked together to piece together an understanding of this rare cosmic visitor. As the comet moved closer to the Sun, its coma, the cloud of gas and dust surrounding it, changed shape and grew more active, offering even more valuable data to those watching closely. But then came an unexpected turn, a gap in the observation schedule. Several of the West's major telescopes suddenly went offline. Some cited technical problems, others were due for scheduled maintenance, and others yet faced issues with observing time slots. As the world's most prestigious space observatories went dark, the astronomical community watched in uncertainty. This moment, when Western facilities were silenced, is when China's observatories rose to the occasion. The timing couldn't have been more critical, as China's telescopes quickly filled the void, offering new images of 3I/ATLAS. At a pivotal moment when the Western astronomical community faltered, China's space program seized the opportunity to step in. Chinese observatories, equipped with state-of-the-art wide-field, high-resolution telescopes, immediately began capturing images of 3I/ATLAS with remarkable clarity and precision. These telescopes, some of the most advanced in the world, are capable of observing not just the comet's morphology, but also its environment, including the surrounding stellar fields. As Western facilities remained offline, China's observatories offered a fresh perspective on the comet's coma, its tail structures, and the plumes of dust and gas emanating from the nucleus. These new frames gave scientists a critical window into the comet's behavior at a time when many other observatories were unable to make observations. The release of these images not only filled the gap left by Western telescopes, but also provided new data that pushed the understanding of 3I/ATLAS forward. The high-resolution images from China allowed scientists to examine the comet's evolving morphology, how its outgassing changed as it approached perihelion, the closest point to the Sun in its orbit, and how its dust-to-gas ratio shifted. These observations were critical in studying the comet's evolution, and the fact that they came from Chinese observatories at a moment when others were absent placed China in a unique position to assert leadership in the global astronomical community. While these images were a scientific boon, they also raised questions about the control of astronomical data. Who controls the narrative surrounding such a unique celestial event? When one country controls critical observational data, it has the power to shape the story and influence future research. By releasing these images while Western telescopes were silenced, China showcased not just technical prowess, but also a clear geopolitical message. China is an emerging force in space science. Their ability to act swiftly and decisively during a critical observation window reinforced the idea that power in space observation is shifting. The Chinese intervention with Comet 3 I/ATLAS is more than just a scientific achievement. It is a strategic maneuver that has implications for the future of space science and global power dynamics. Control of astronomical data is an often overlooked but vital aspect of space exploration. By securing images and data from 3 I/ATLAS, China not only contributed valuable scientific information, but also gained influence over how the comet story would be told. Early access to data allows a nation to frame the narrative, emphasizing certain features or anomalies, which in turn guides the direction of future research. In the world of scientific discovery, early publication is crucial. The first group to release data often gains prestige, citations, and recognition, which can shape the direction of a study for years to come. China's release of these critical images could give Chinese astronomers an edge in shaping the models and theories surrounding 3 I/ATLAS. As the comet's data is analyzed, Chinese teams may find themselves at the forefront of research into its composition, trajectory, and interactions with solar radiation. This gives them an opportunity to lead in a rapidly growing field and to assert dominance in an area that has long been dominated by Western powers. The geopolitical implications of this event are hard to ignore. Space exploration is not just about science, it is also about national pride and power. With their space program rapidly expanding and gaining sophistication, China is positioning itself as a leader in space science. And the timing of this event couldn't have been more perfect. By stepping in when Western telescopes faltered, China not only secured scientific credibility, but also showcased its technical capability and leadership in deep space monitoring. This move has the potential to change how the world views China's role in the international scientific community, especially as the country continues to assert itself on the global stage. While the Chinese images have undoubtedly enriched the global scientific data set, they also highlight the limitations of relying on a single source of data. For an object as rare and dynamic as 3 I/ATLAS, comprehensive data from multiple telescopes across different wavelengths is essential. The best scientific conclusions come from a broad, multifaceted approach, utilizing data from optical, infrared, ultraviolet, and even radio telescopes to build a complete picture of an object's behavior. The lack of concurrent observations from Western telescopes, combined with the absence of multi-wavelength data, creates a gap in the global understanding of 3 I/ATLAS. The issue of calibration is another concern. Different observatories use different instruments, which can lead to discrepancies in the data. The filters, exposure times, and response characteristics of Chinese telescopes may differ from those of Western facilities, making it difficult to directly compare the data without careful adjustments. This lack of uniformity complicates efforts to integrate Chinese data into the global scientific narrative. While China's observations are valuable, they cannot be seen as a complete or definitive record of the comet's behavior. There is also the risk of overinterpretation. When data is limited, especially in a fast-evolving context like that of Comet 3 I/ATLAS, there is a temptation to draw conclusions too quickly. Without comprehensive cross-disciplinary observations, the interpretations made from the Chinese data may be incomplete or biased. For instance, the Chinese observations might suggest certain features or anomalies that could be clarified or refuted by follow-up data from other observatories. The danger is that premature interpretations could shape the global understanding of the comet before all the facts are in. While the Chinese images of Comet 3 I/ATLAS are undoubtedly valuable, they also underscore the inherent limitations of relying on a single set of data. The complexity of the comet's behavior and composition requires a multifaceted approach, with data gathered from multiple observatories across different wavelengths: optical, infrared, ultraviolet, and even radio waves. Each of these wavelengths provides unique insights into different aspects of the comet's nature. For instance, optical data reveals details about the comet's coma and tail, while infrared observations can detect temperature variations and the distribution of dust particles. Ultraviolet data, meanwhile, offers critical information about the comet's outgassing process and its chemical composition. The problem with relying solely on the Chinese data is that it provides only one piece of the puzzle. As 3I/ATLAS evolves over time, particularly as it approaches perihelion, its closest point to the Sun, its behavior changes rapidly. The dust-to-gas ratio shifts, new jets of material might emerge, and the comet's morphology may warp due to the pressure from solar radiation. Without continuous cross-disciplinary observations, it's difficult to draw accurate conclusions about these phenomena. A more comprehensive view would require data from a variety of instruments, from optical telescopes to infrared surveys to multi-wavelength spectrometers. Without these complementary data streams, the Chinese data alone may lead to incomplete or even misleading interpretations of the comet's behavior. Moreover, calibration discrepancies between different observatories are another significant challenge. Chinese telescopes use different instruments and observational techniques compared to their Western counterparts. Differences in exposure times, filters, and response characteristics can result in data that is not directly comparable. This makes it more difficult to combine Chinese observations with data from other sources without carefully adjusting for these variances. This lack of standardization complicates the process of integrating different data sets into a coherent scientific narrative. In addition to these technical challenges, the issue of interpretation arises. With limited data, scientists may be tempted to make conclusions based on incomplete evidence, particularly when the comet is undergoing rapid changes. For example, the Chinese images may suggest certain features or anomalies, such as jets of gas or irregularities in the dust trail, but without cross-referencing with infrared or multi-wavelength data, these observations may be misinterpreted. The temptation to construct a grand narrative from limited data could result in premature theories that later need to be revised when more data becomes available. Thus, while the Chinese data has filled a critical gap, it is essential that this data be treated with caution. Full integration of Chinese images with data from other observatories will be required to build a complete and accurate understanding of Comet 3I/ATLAS. Only by cross-referencing different observations across multiple wavelengths will the scientific community be able to gain a truly comprehensive view of this extraordinary interstellar visitor. The global response to China's sudden leadership in the observation of Comet 3I/ATLAS has been mixed but revealing. For decades, the astronomical community has been dominated by a handful of Western institutions, such as NASA, ESA, and several prominent observatories in Chile, Hawaii, and Europe. These institutions have long enjoyed the prestige, funding, and resources necessary to make groundbreaking discoveries in space science. However, the temporary failure of some of these key observatories during critical observation periods for 3I/ATLAS exposed a vulnerability in the global scientific infrastructure. The gap left by these Western observatories forced the scientific community to consider the fragility of its infrastructure. Space science is deeply dependent on large, centralized telescopes that, while highly capable, are vulnerable to logistical failures, maintenance schedules, and technical issues. The fact that major observatories were unable to observe one of the most important interstellar objects in recent history underscores a growing issue in space science. A reliance on a few key facilities that, when unavailable, leave gaps in data. The recent situation highlights the need for greater redundancy in observational infrastructure, especially when studying rare events that cannot be repeated. The space science community must now consider how to distribute observation capabilities more equitably across the globe to ensure continuous monitoring of celestial phenomena, even when one or two observatories experience downtime. China's intervention in this scenario has sparked significant discussions about the future of space observation. China's growing space program has positioned the country as an increasingly important player in global astronomy. Their response to the gap left by Western observatories has raised questions about the dominance of Western space institutions in the scientific community. While some celebrate China's role in filling the observational gap, others worry about the geopolitical implications of this shift. If one nation can step in and control critical periods of observation, it raises concerns about data access, ownership, and interpretation. Will data from Chinese observatories be freely shared with the global community? Or will access be restricted to China's internal scientific teams? These questions have the potential to shape the future of collaboration in space science, particularly when it comes to sensitive data regarding rare objects like Comet 3I/ATLAS. At the same time, China's actions have highlighted the need for more inclusive global collaboration in space science. Other countries, including those in Asia, South America, and Africa, are rapidly investing in space infrastructure, and this trend could provide a counterbalance to the dominance of Western institutions. A more diversified network of observatories across the globe would provide greater resilience in the face of technical failures and logistical challenges. However, this diversification also requires greater coordination, transparency, and data sharing practices. Without clear standards for how data is shared and accessed, the global community risks a fragmented, competitive scientific environment where certain countries dominate key discoveries. In the wake of this shift, there will likely be increased pressure for collaboration between Western and Chinese observatories. As China continues to strengthen its position in the space science community, it is essential that international partnerships be formed to ensure that scientific discovery remains open and inclusive. The challenge now is finding a balance between national pride, scientific collaboration, and transparency in data sharing. The recent developments surrounding Comet 3I/ATLAS provide a significant opportunity for reflection within the global scientific community. The event has underscored several important lessons about the future of space science and the vulnerabilities within the existing infrastructure. First and foremost, the importance of infrastructure redundancy has become glaringly obvious. Space science has traditionally been reliant on a few key institutions, but the recent gap in observation caused by the downtime of Western telescopes illustrates the risks of this centralized system. The scientific community has learned that no single observatory, regardless of its prestige or capability, should hold too much sway in the study of transient celestial phenomena. The comet's fleeting nature makes it imperative that data is continuously collected and that observational efforts are well coordinated across different facilities. This lesson calls for greater diversification in the global space science infrastructure. More observatories, especially those in underrepresented regions like Asia, South America, and Africa, are needed to ensure that rare events like 3I/ATLAS can be captured from multiple angles across a range of wavelengths. Having a distributed network of observatories, both large and small, ensures that if one facility goes offline, others can immediately step in to continue the work. This system would not only enhance the continuity of scientific observations, but also prevent data gaps during critical periods. China's swift response to the gap left by Western telescopes has highlighted the importance of having flexible, well-funded observatories that can act rapidly when needed. Another important lesson from this event revolves around the sharing and accessibility of data. The Chinese release of Comet 3I/ATLAS images raised questions about the ownership and control of scientific data. In an increasingly competitive global environment, where nations vie for scientific prestige, the question of who controls data becomes increasingly important. Will the data collected by Chinese observatories be shared freely with the global scientific community, or will it be restricted to internal use? The scientific community must ensure that data access is equitable and transparent to prevent a situation where only one nation's interpretation of events dominates the narrative. Open, timely data sharing is essential for ensuring that discoveries are made collectively rather than being monopolized by any one nation or institution. Perhaps the most important lesson to be learned from this moment is the need for agility in space science. With the increasing pace of technological advancement and the rise of transient astronomical phenomena, the traditional model of scheduled observations and fixed timelines is no longer sufficient. Space science must become more flexible, able to pivot and adjust quickly to fleeting opportunities. As we saw with 3I/ATLAS, the ability to capture data at the right moment is paramount. Nations with the agility to observe in real time, regardless of technical difficulties or maintenance schedules, will have a distinct advantage in future discoveries. This shift toward more agile, responsive observation strategies is essential if we are to fully capture and understand rare events in space. As we conclude our examination of Comet 3I/ATLAS and the shifting landscape of space science, it is clear that this moment marks a significant turning point in the field. The release of data by Chinese observatories during a critical gap left by Western telescopes has forced the scientific community to reckon with the vulnerabilities in its infrastructure. The importance of infrastructure redundancy, data sharing, and agility has never been more apparent. In an era of rapidly advancing technology and fleeting opportunities, space science must adapt to ensure that no key observation is missed, no critical window of discovery is lost. The events surrounding 3I/ATLAS serve as a wake-up call for the astronomical community. For too long, space science has relied heavily on a few well-established observatories. The gap left by Western telescopes during this critical period exposed the risks of such reliance. To avoid future disruptions, it is essential that the global community invest in more distributed, resilient infrastructure. Countries like China, India, and those in South America and Africa must continue to build and expand their space programs to provide a more diversified network of observatories capable of capturing key data without interruption. This distributed network will be crucial in ensuring that rare events like interstellar comets are fully observed and understood. Moreover, the events surrounding this comet highlight the growing competition in space science, where nations vie for both scientific leadership and geopolitical influence. The ability to control key data gives countries like China significant leverage in shaping the narrative of astronomical discoveries. As the global community moves forward, it must ensure that data access remains open, transparent, and equitable, allowing for collaboration across borders, and ensuring that no nation can monopolize the story of our universe. This shift also underscores the need for agility in space science. The next great discovery may not happen when we expect it, and it may not be observed by the facilities we rely on today. The Comet 3 I/ATLAS incident is a stark reminder that we must be prepared to adapt quickly, to step in and capture data in real time, and to be ready for whatever the universe throws our way. The future of space science is no longer about relying on a few dominant institutions. It's about building a more inclusive, collaborative, and resilient global network of observatories, one that can capture every fleeting moment of discovery. Only by doing so can we truly unlock the mysteries of the universe and ensure that no critical event is left behind. The unfolding story of Comet 3 I/ATLAS has revealed a major shift in the dynamics of space science. For decades, the astronomical community has been led by a few key Western observatories, with much of the discovery and data sharing controlled by a handful of institutions. However, the unexpected intervention of Chinese observatories during a critical observational gap has highlighted the vulnerabilities and limitations of the system. With China stepping in to fill the void, questions about data ownership, global access, and the future of space exploration have come to the forefront. This incident signals the need for a more resilient, diversified network of observatories that can provide continuous global coverage for rare phenomena. As space science evolves, collaboration will be key, but so will the ability to adapt quickly and strategically. The question now is, how will the scientific community respond to this shift? Will it lead to more openness and cooperation, or heightened competition? Let us know your thoughts in the comments below, and don't forget to like and subscribe for more insightful updates.